Hello everyone. Today we will learn about accelerating and rotating fluid. This is a very important concept for JEE Mains and JEE Advanced. So first of all, we will learn about some basic concepts, review some basic concepts, and then we will deal with some standard problems. So let's start. So first of all, we have to see the pressure variation in a fluid with depth. So you must be knowing this, that let's say there is a container and it contains some fluid which has a density of rho. This is point A and this is point B, and depth of the point B is h. Atmospheric pressure is P naught. So you must be knowing that PB equal to PA plus rho GH, where G is the acceleration due to gravity, right? So we can easily derive this equation. We will take a container which contains the same fluid rho, having density rho, and we will consider a cylinder, a cylindrical element of the fluid. So the pressure is P1 here and pressure is P2 here. So isolate the cylinder. So due to this pressure P2, a force is acting on the cylindrical surface, that is F2, and here the force is F1. The height of the cylinder, take it to be h, and area is A. The cross-sectional area is A. So if you make the free body diagram of the cylinder, it is like this: F1 acting from above, F2 from the bottom, and mg is the mass of the cylinder. So the cylinder is in rest. The forces must be balanced. F1 plus mg must be equals to F2, right? But we know that what is pressure? Pressure is just force per unit area. So force is pressure times area. So what is F2? F2 is P2 times A, and F1 is P1 times A. So F1 can be written as P1 times A plus mg equal to P2 times A, F2, right? So what is m here? Mass of the cylinder. So we know that the volume of the cylinder is area times its length, h, right? And we know that rho is mass times volumes. So mass is rho times v, that is rho times ah, right? So if we put here mass equals to rho ah, g equals to P2a, a cancels out, and we get P2 equal to P1 plus rho gh. So we have derived this equation, right? Here I have taken point A and B, but here the point A is taken as P1 and B is taken to be P2. This is the same thing, right? So now we see another case where the container is kept in an elevator. The elevator is going upward with acceleration A, and some fluid is filled here. This is point A, this is point B, and the question is same: PB minus PA is what? So in this case, what we do is just attach the observer with the cylinder, with the container, and what will happen? The fluid is already experiencing a acceleration due to gravity g, but now as the observer is attached to the container, the fluid will be experiencing acceleration of a, because the container has acceleration of a upwards. So if the observer sits on the container, it will see the fluid experiencing acceleration a downwards. This concept I have explained in my previous video, so you can watch it from there. So what we have to do is just attach the observer to the container and see the fluid from there. So the fluid is experiencing a net acceleration of g plus a. Now this is a, this is b, and h is the difference. Now what we can do? Pb equal to Pa plus rho g plus a times h. Look here, the acceleration due to gravity was g, so the only g comes here, but here the effective acceleration is g plus a. So G plus A will come here, and there will be no change in equation. So this is the final expression. Now, if the elevator is going downwards, let's say the elevator is going downwards, everything is same, just the elevator is going downwards. Now, what will you do? Do the same thing, right? Just attach the observer to the container. The observer will see the acceleration of the fluid to be G downwards and A upwards, right? Because the acceleration of the container was A downwards. So if you see with respect to the container, everything will have the acceleration of A upwards, right? We have seen this concept. Let's say I have a car which is moving with VA, and I have another car which is moving with VB. Now, if I attach an observer to this car will come at rest. A will be at rest. And what will happen to B? In this frame of reference, B will have its original velocity, but what will this observer will observe that this B has additional velocity, which is VA in opposite direction. Just give the velocity of A to B in opposite direction. So this observer will see the velocity of B to be VB minus VA, right? So we are doing the same thing here also. We are doing this with acceleration. This is true with acceleration as well as velocity, right? So here the effective acceleration is G minus A. So PB equals to PA plus rho times G minus A into H. So in this manner, we can solve the problem of accelerating fluid, right? Let's say there is a tube. Now there is no gravity. Let's say this is all happening in space, and this fluid is accelerating with acceleration A here. This tube is accelerating with acceleration A in rightward direction, and this is point A and this is point B, and length is L, right? So the same thing we have to find. PB minus PA is what? So do the same thing. Take this tube at rest. Let's attach the observer to the tube. So the observer will see that fluid has the acceleration of A in opposite direction, right? So it is simple, right? PB will be equal to PA plus rho AL, because we are moving in this direction. If you move in the direction of the acceleration, the pressure will increase. So PB equal to PA plus rho AL. So in the case of constant acceleration, we have to do just that. We have to attach the observer to the container, see the fluid from this reference frame, and just write this equation, right? So if you move in the direction of acceleration, the pressure will increase. If you move opposite to the direction of acceleration, then the pressure will decrease. But this acceleration is from the reference frame of this observer, which is attached to this tube. Always remember this. Now, I can ask you a problem. Let's say there is a container, and this container is accelerating with acceleration A in rightward direction. So the water will be like this. The water surface will be slant. You might have seen in your everyday life, this happens, right? We have to find out the angle of this slant, theta. To solve this, what we can do is attach the observer to the container. Fluid has acceleration due to gravity G in this direction, and A will come here because the container has an acceleration in this direction. So this observer will see the fluid accelerating in this direction, right? Okay. So let this point to be A, this point to be B, and this point to be C. Okay. P0 is the atmospheric pressure. Now we have to see this. If you come along this line BC, the only effect will be of G, right? The acceleration that will be contributing to the pressure increase will be G, not A, because A is in perpendicular direction to BC. Okay, so A will have no effect if you come along this line BC. If you move along this AC line, the A will contribute, this acceleration A will contribute, there will be no contribution of G. So if you want to write the pressure at a point C, PC, first you write the pressure at point B, that will be P naught, simply because it is in contact with the atmosphere, right? Take this height as H, so P naught plus rho GH, and take AC as L. Now write PC along this line AC. So pressure at point A is also P naught, because the point A, this point, is also in contact with atmosphere, right? And acceleration that will be contributing to this pressure increase will be A, so rho AL. But point C can't have two distinct pressure, right? They must have, they must take they must take same values, right? This PC is equals to this PC, so this whole thing is equal to this whole thing. So equate this, rho GH equals to P naught plus rho AL. P naught cancels out, rho cancels out. We are left with GH equal to AL. H upon L is A upon G. So we can see that this is theta. So tan theta is H upon L. And here we are getting H upon L. So tan theta is A upon G. So theta is tan inverse A upon G. So this is a standard problem that is very simple to solve. So now let's see the case of rotating fluid. So what if fluid is rotating? So let's say there is a tube, and the tube is connected with an axis, and the tube is being rotated with omega, angular speed omega, and some kind of a fluid is filled here, and this is point B, this is point A, and the rho is the density of the fluid. We have to find PB minus PA. So here, what is the difference between this case and this case? Here, at every point, the acceleration is different. The fluid is experiencing distinct acceleration at every point. Go at this point, you will find that fluid is experiencing omega square x, where x is the distance from the axis, right? In circular motion, in rotating frame, you see that the fluid is experiencing acceleration omega square x. But if you move here, come to this point, the x will increase, so that acceleration will also increase. Therefore, we cannot do directly rho GH like this, rho AL. Okay, so we have to take element and integrate. So what we can do is, this is omega, go to a point x from the axis, take element of dx, and for this small element dx we can write, because for this small element dx the acceleration is approximately same. You can consider acceleration to be same because dx is small, very very small, right? So acceleration for this whole element is omega square x, because this whole element is at x from the axis, right? So this is dx. So we can write the pressure difference between this its end, that will be dp. dp is rho omega square x dx. This is same as writing delta p or pb minus pa rho gh, right? Here, in place of g, we are writing omega square x because acceleration is omega square x. In place of h, we are writing dx because length is dx. Now we have to integrate this. dp integration rho omega square x dx from pa to pb. And this is from 0 to L, because the length is L, right? The length is L. The length of the tube is L. So pb minus pa will come out to be rho omega square is constant, and x dx is being integrated from 0 to L. So rho omega square L square upon 2, right? So pb minus pa is rho omega square L square by 2. So this is the result of the pressure difference when the rod is rotating. Not rod, it's a tube. Yeah, so tube is filled with the fluid and the tube is rotating, and the pressure variation is like this, omega square L square rho upon 2. So there are many interesting problems based on this, right? So now let's come to this problem. This is a problem which says that initially there are 3 tubes, 1, 2 and 3, and about 1 first tube, this whole container is rotated with angular speed omega. And initially, the tube has the water level of h, height h, and the total height is h, and this is A and this is B. These all are given. So we have to find the height of water level in the tube 1, 2, and 3 after some time. Means when this container is rotated about 1, the water level will change, right? The water level in the tube 2 will go up, and in tube 3, the water level also will go up. But in tube 1, the water level will come down. So the diagram will be like this. So let's say the water level is H1 in tube 1, H2 in tube 2, and H3 in tube 3. So consider point A, B, and C here. Now what we can do is we can write the pressure at point B. Point B. So if you see, if you come along vertical direction, so there is a gravity, right? So there is a G downwards. So rho G H1 is the pressure, right? And I have assumed the atmospheric pressure to be negligible, or you can take it as a P naught, but it will cancel out, right? In all the previous cases, it cancels out, so it will cancel out. So you can just ignore it or take it as a P naught. If you take it as a P naught, it will become P naught plus rho G H1. So you will see that atmospheric pressure will cancel out in next following equations. So pressure at point A is what? Rho G H2. If you go along this vertical direction, the pressure is rho G H2. But you can also go along this direction, right? From B to A. So at a point B, the pressure is rho G H1. But if you go along this line AB, then we can use that result that we derived here, right? So this is rotating, and this is like a tube of length A, right? So the pressure here will be larger, okay? The pressure at point A is larger by how much amount? This much amount, half rho omega square A square. Just like this, using this result, rho square omega square L square by 2 for this question, we can use that result here also. So therefore PA will be rho GH1 plus half rho omega square A square, right? Similarly PC, if you go along vertical direction, it will be rho GH3. If you go along horizontal direction from point B, it will be rho GH1, which is the pressure at point B, plus half rho omega square B square, because this distance is B, right? This distance is B. So now this 2 will be equal and this 2 will be equal, right? So before equating this, we can conserve volume also. Observe that in initial condition, the lower tube is filled. In final condition also, final case, the lower tube is completely filled and there is no change in the lower part of the tube, right? So there is only change in this part of the container. So now initially, let's assume that cross-sectional area of these tubes are A, and all three are equal. So cross-section of this tube is A, this tube is A, and this tube is also A. So the volume of this much part is HA, and similarly for this part and similarly for this part. So the water contained in this part plus this part plus this part is 3 times H times A, right? 3HA. So the water content here in final condition will be like this: H2A, H1A, and H3A. And this must be equal, right? Because the volume of water must be conserved. Water is not spilling out from the container, so the volume is conserved, right? So H1A plus H2A plus H3A equal to 3HA. Now A will cancel out, so H1 plus H2 plus H3 equals to 3H. Now from here we can equate this, because PA, this both are PA. So from here we get rho GH2 equal to rho GH1 plus half rho omega square A square. So H2 minus H1 is what? Omega square A square by 2G. Just rearrange these terms, and from there we can find out H2 equal to this expression, H1 plus omega square A square plus divided by 2G. Similarly, you can equate these two equations, right? And we get H3 in terms of H1. Now we have three equations, right? This equation, and this equation, and we have three variables, so we can solve it, right? So replace this H2 and H3 with H1 here in this equation. So put it here and you will get this equation. From here we can find out H1. H1 comes out to be this much, and now we can find out H2 as well as H3. So H2 comes out to be this much and H3 is this. So we have found out H1, H2, and H3, the water level in all three containers, right? So this is the way to solve, and this is the application of rotating fluid. This is the application of this derivation, right? This formula. So this type of question can be asked in your examination. So let's move on to second part of the question. Find the maximum angular speed with which the tube 1 can be rotated so that the water does not spills out of the vessel. Means the maximum omega, just think about it. When omega increases, the water in this first tube will decrease and the water level in third and second will increase. But in the third tube, the water level will increase faster, right? It will be higher than in compared to tube 2 because the pressure here is larger. You can see that this distance is large, so the pressure is larger, half rho omega square b square. So b square is large compared to a, so pressure here at c is larger, so the height should be larger as well to compensate for this pressure, right? Rho g h3 must be equal to this rho g h1 plus half rho omega square b square. So water will spill out from the tube 3 first. Okay, I hope you understand this. Now we have found out h3, right, in terms of omega square, and h is constant. H is the initial value of the water level. So putting h3 equal to h, we can find out omega, right? We can find out omega, and omega comes out to be this, and this will be maximum omega with which the vessel can be rotated without the water being spilled out, right? If you increase the omega beyond this limit, the water will spill out. I hope you understand this question and the application of rotating fluid. So now I have this question. This is a classic problem of rotating fluid. So there is a container. This is the container, and container contains some kind of fluid which have a density of rho, right? And this container is rotated about this mid-axis with angular speed omega. The container has a height of h and the length of a and breadth of a. The base has the area of a. This container is like this. This is just a cross section, and the water is filled up to height 2h by 3. Now, find, like, the question is draw the shape of the water and find the equation of the curve. So intuitively, you can think the shape of the water will be something like this. It will assume the shape like this. You must have seen in your everyday life in bucket or something like that. When water rotates, it kind of assume the shape of a parabola, right? But we don't know. We have to find the equation of the curve, right, to confirm this. So let's assume the shape is like this. Now mark point A, point B, and point C here, and P naught is the atmospheric pressure. So PA is P naught because A is exposed to atmosphere, right? At point B also the pressure is P naught. Now from A you move to point C. So you are moving in horizontal direction, and there is one acceleration in horizontal direction, that is omega square x, right? And this is a rotating fluid. So the pressure difference between this point is what? Half rho omega square x square. We have seen this, right? So PC will be P naught plus half rho omega square x square because PA is P naught. So P naught plus half rho omega square x square. Now along this line BC, you come along this line BC. There is only one acceleration in vertical direction, that is G. So the PC will be P naught plus rho gy, right? And x and y is the general point on the curve. Okay, and y is this distance and x is this distance, and A is the origin, right? This is x-axis, this is y-axis. Okay, so we have to equate this because this must be equal, right? PC equal to this, PC equals to this. So if we equate this, P naught will cancel out, rho will cancel out. We will find that y equals to omega square x square upon 2g, and this is the equation of a parabola. We have to find the equation of the curve. Equation of the curve is what? Relation between x and y. So we have found out the relation between x and y. So this is the equation of the parabola. So this curve is a parabola, right? But this is just a cross section. If you see in 3D, then this will be a paraboloid, right? So what is the next question? What is the minimum value of omega such that we can just see the bottom of the container? We want to see the bottom of the container. So think about it. If you increase the omega, this parabola will become like this, right? If you keeps on increasing omega, somewhere it will become like this. Here is the proper diagram. So we have to find out the value of omega for which the bottom is just visible, means the shape of the parabola is like this. Okay, we know the equation, right? Y equal to omega square x square by 2g, and now we can put it here in the equation, right? This is the origin, so this point is a by 2. So for x equal to a by 2, y must be h, right? So put it here in the equation, y equals to h and x equal to a by 2. It must satisfy the equation, right? So from there we can find out omega, and omega comes out to be this. So this is the minimum omega for which we can see just the bottom. If you increase the omega, the water will further spill out. and we can see the bottom clearly, right? But we have to find the minimum omega. So this is the answer. Now, the third part, find the volume of the water spilled out. So in this case, some water is spilled out, some amount of water is already spilled out, right? So we have to find out the volume of the water spilled out. So how to approach this problem? First of all, we find out the initial volume of the water contained in the container. And then we have to find out the final volume of the water contained in the container. And just subtract these two. First of all, we have to see what is the volume of the paraboloid. Let's assume this is a paraboloid, and this is R, and this is H. The volume of this paraboloid is given by half pi r square h. So in our case, this is a paraboloid, right? The radius is a by 2, and the height is h. So the volume is, just put the values, half pi a by 2 whole square h, and this comes out to be 1 by 8 pi a square h. Now, the volume of the water left. What will be the volume of the water left? So, first of all, find out the volume of this whole container. The volume of this whole container is a square h, because the base area is a square and this height is h. So a square h. And if you subtract this volume of paraboloid, the remaining volume will be the volume of the water. So the volume of the water left will be a square h minus 1 by 8 pi a square h. Now the volume of the water initially present is 2h by 3 a square, because height of the water level is 2h by 3 and area of the base is a square. Now the volume of water spilled out is initial volume minus final volume. This is very simple, right? Initial volume minus final volume. Initial volume is this much, final volume is this much. You just subtract this, solve and simplify, you will get this answer, pi by 8 minus 1 by 3 a square h. Okay, so I hope you understood these questions, and if you have some doubt, please let me know in the comments. So thank you.